The fundamental theorem of calculus part 1 says that if I have a continuous function little f, I can build an antiderivative of it by taking the net area function from a to x of little f of t. I want to prove this part of the fundamental theorem of calculus part 1. I want to prove that when I take the derivative of this function, I get back little f. I'll talk about the fact that this new function is both continuous and differentiable on the respective closed and open intervals. But so far as this video, I'm only going to prove that the derivative of the given function, big F of x, is little f. So, we know that big F of x is equal to the definite integral from a to x of f of t dt. I'm going to find the derivative the only way I know how, when I don't have a nice rule like the quotient rule or product rule you use. I have to use the definition of derivative. So I need to take the limit as h approaches 0 of f of x plus h minus big F of x all over h. So again, the derivative of big F is the limit as h approaches 0 of big F of x plus h minus big F of x all over h. So big F is a definite integral. Whatever goes in here becomes my top bound, little f of t dt. And I'm supposed to be dividing by h, but I think what I'm going to do instead is go on and rewrite that as a multiplication by 1 over h. Well, on this first definite integral, I'm going to think of the additivity property as saying that this integral is the same as the sum of these two integrals. And of course, all three now times 1 over h. Right, integrating from a to x, and then adding the integral from x to x plus h, additivity tells me is the same thing as integrating from a to x plus h. Well, what I see now is that this part and the second part cancel. You can also very cleverly think of these as canceling areas to get to this one. But now I have a much easier statement to understand. I have 1 over h times the definite integral from x to x plus h of f of t dt. And I want to think about this statement. I know f is a continuous function. I was told that in the hypotheses of the theorem. And x to x plus h is a finite closed interval. So the average value of f on that interval is 1 over, and I should subtract the two endpoints. Well, x plus h minus x is just h, times the definite integral over that whole interval. So this calculation right here is just the average value of f over this particular interval. Well, I know from the mean value theorem for the definite integral that that means there is a function value, so there exists some c, so that f of c equals the average value of f, and c has to be on the interval from x to x plus h. So I can replace this with that particular function value, right? F of c, where c is between x and x plus h. So now I have the limit as h approaches 0 of f of c. But what I know about c is that c is somewhere between x and x plus h. Well, I'm taking a limit as h goes to 0, which means x plus h is getting closer to x. So as this value gets closer to x, well, c has to get closer to x as well. So, for a very small value of h, then c would have to be somewhere between. And arbitrarily small keeps getting closer and closer and closer. So as h goes to 0, c is getting closer to x. Because f is a continuous function, that means f of c has to be getting closer to f of x, which means as h goes to 0, f of c becomes f of x. And if I put all of that together, the derivative was equal to this limit. I did a bunch of arithmetic to get here, and this limit was equal to f of x. So the derivative of my cumulative area function, that net area function, is little f of x. And I've proven what I set out to prove. Now the theorem goes on to say that this function, big F of x, not f prime, but big F of x, is continuous on the closed interval and differentiable on the open interval. Well, I've literally taken its derivative on that open interval, so I feel very comfortable with that part. Because I'm differentiable on the open interval, I'm automatically continuous on the open interval. The only thing left to do to prove the full effect of the theorem is to make sure big F is continuous at A and at B. And I'll let that be an exercise for you all. All we would have to do is apply all three parts of the continuity test.